we are working on the product and quotient rule, and that's what we're going to work on today. I'm going to show you some more complicated versions. In particular, we're going to look at questions where the style points, the making them look pretty after the event, is going to be the major challenge. So let's take, I've got a guy floating around here. As soon as I find it, we'll do it. Let's do a product rule with a square root in it. That's the first one I want. Product rule with a square root in it. Yeah, this one will do. So we have a function, and it is a z cubed plus an e to the z multiplied by the square root of z. So it's definitely going to be a product rule, right? It's two things multiplied together. But if I'm going to do a product rule, I have to turn the square root into a half power. Hopefully that's obvious, right? You've done that before, right? You can't find derivatives of square roots easily. You have to turn them into half powers, and then you can do it. And so the derivative is going to be f dash g plus f of g dashed. And in this world, that guy can be the f, and this guy can be the g. So let's see what we get. You differentiate this guy, you get 3z squared plus e to the z, and you leave the other guy alone. Plus, you leave the first guy alone, and you multiply by the derivative of that guy, which is 1/2 z to the negative a half. And I don't know why I did that line there. So we're left with this guy here. As much as you would want to, you're not allowed to leave it hanging like that. Don't we have what I call style points, which means what? Collect like terms, factor the heck out of it, right? Make it look like the original, those kind of rules. What do you think I need to do first on this question? What do you think I need to do first? Yeah,
distribute.
Yeah, distribute. So 3z to the half times z to the half gets you 3z to the 2 halves, which is 5 halves. E to the z times that guy is e to the z, z to the half. Plus, this guy times this guy gets you 1/2. 3 take away a half is 2.5, so that's z to the 5 halves. And this guy times this guy gets me 1/2 and e to the z, z to the negative 1/2. Now, there's not an awful lot going on, but this guy and this guy can be combined. And what does that get me? It gets me 3.5 z to the power 2.5. And then I have an e to the z, z to the half. And then I have 1/2 e to the z, z to the negative a half. This expression, you might think that's about it. Can't do anything else. I've collected the like terms. I could turn these guys into various versions of square roots. That one would be a fractional version. Surely that's the best you can expect me to do. And the answer is no, it's not. I'm now going to show you an algebra technique that you may never have seen before. Common factors with negative powers. You can actually have negative powers of x or z as a common factor. You're used to x cubed and x squared, right? If I gave you that, I would hope you would say 3x squared is a common factor and x add 2 would be left. Great. Now, when you have powers of x in all the terms, you know that you can pull out a common factor of a power of x. The choices in this question were x cubed and x squared. The one that you pick is always the smaller of the two choices. Great. Now, change the letter just because we can. T to the 4, 2t cubed plus 5t. You can pull out a common factor if there's 3 terms, as long as they all share a power of t. And in this case, wouldn't it just be 1t? The smaller of the 3 choices. And you pull out the t, and you'll be left with a t cubed, a 2t squared, and a plus 5. I am going to do the same thing to this expression. I notice that each term has a power of z. Do you notice the power is 5 halves, the power is 1 half, and the power is negative 1 half? That means I can pull out a power of z. And the common factor you pull out is the smaller of the 3, negative a half. I don't know how many of you, if any of you, have ever pulled out a negative power as a common factor, but it is allowed. So you are allowed to do it, right? As they all have powers of z. The fact that one of them is negative doesn't mean it can't be used as a common factor. Well, let's see what you get left. I'm going to do the last one first. If you take out this guy as a common factor, would you agree you just got half e to the z? You have used it all up, right? Now, if you were doing this question, I would say something like this. X squared, right? I'd say x cubed, take away an x squared. In fact, wouldn't I just say 3 take away 2 leaves 1 power? In this one, I'd say 4 take away 1 leaves 3 powers. This guy is going to be 7 over 2. 5 halves take away negative a half. 5 halves subtract negative a half. What do you get as a power when you do that?
Cube.
5 halves.
3.
So again, is it squared? You're adding it. 5 halves take away negative a half is 5 halves add a half.
So cube.
You got cubed. And check it out. If you multiply these two together, wasn't 3 take away half gets you 2.5? Is it? Z cubed, z to negative a half, 3 take away a half is 2.5. Right. Okay, next one. 1 half, take away that power. 1 half, take away a negative a half. What do you get from that guy?
You're just adding up to 1, so you don't have to write a power anymore.
So you get Z. I think there's 3 homework questions where this weird pulling out a negative power happened. This is one of the 3. So far, so good? Right. Now, negative a half power. Can't I just stick it on the bottom? Like that. Great. Now, there's something else I could have done, and I guess I got lazy and didn't, is that when I look at that top, would you agree that 7 halves and a half are kind of clunky? They just kind of make it look slightly ugly. So what I'm going to do is I'm going to pull out a half as a common factor. And that makes this funny guy in the middle suddenly become 2. And the reason it needs to be 2 is, isn't a half times 2 going to get you back to the original? And I don't like that half where it is. I'm going to bring it downstairs as a 2. And while I'm at it, I'll turn that into a square root. So our final answer was 7z cubed plus 2e to the z. I guess we have z. Plus an e to the z. And on the bottom, 2 square roots of z. So that is an algebra skill that isn't common. You don't do a lot of them. As I said, there's definitely one more. There might be another one more. There's 2 or 3 where this happens. There's definitely one of them. You're looking at it, but there's 2 or 3 where this could happen, and you just have to work on it quite a lot. But the trick is to realize that you can pull out negative powers as common factors. As long as you can do the process, you'll be fine. I'll leave that for a few seconds. Try to see if I can find a, yes, here's one. Next question we're going to do is a quotient rule. The quotient rule that we're going to do is for this cube root of t over t take away 9. Minor cosmetic surgery. The cube root is going to be written as t to the power of 1/3. So there's the top. There's my f and my g. So my derivative of f dash g take away f of g dashed over g squared. If you differentiate t to the 1/3, you get 1/3 t to the negative 2/3, right? Multiply by the power, reduce it by 1. Leave the other guy alone. Take away, leave him alone, and differentiate. Oh, just get 1. And the whole thing on the bottom gets squared. So f dashed g take away f g dashed. I'm going to distribute 1/3 t to the negative 2/3 times t gets you 1/3 t to the positive 1/3. Are you happy about a negative 2/3 times a t gets you a positive 1/3 power? And this guy times this guy gets you negative 3 t to the negative 2/3. And this guy at the end gets you negative t to the 1/3. All over t minus 9 squared. These two combine. So what I've now got is this fella take away this fella. I'm just rewriting this guy again at the top here. Same problem as last time. I can pull out a common factor on the top. And the choices are, it's either t to the negative 2/3 is my common factor, or it will be t to the positive 1/3, right? One of these two is going to be my common factor. Which one is it? Which one of these two is going to be my common factor in this question?
T to the negative 2/3.
Agreed. It's always the smaller of the two. So negative 2/3 is smaller, colder. Now, if you pull it out of this fella, you get negative 3. In this second guy, you get negative 2/3. Now, take the power, 1/3, and subtract negative 2/3 from it. So 1/3 subtract negative 2/3. Don't they just add together and get you t to the 1? Are you happy about where that t came from? 1/3 take away negative 2/3. Right. Basically, you always suck out a common factor, right? You remove it from the original power. Well, if it's negative, removing a negative is like adding it, isn't it? So you get 1/3, add 2/3, 3/3, 1. Now, negative 3, take away 2/3 t, and on the bottom, 2/3, that guy. Do you like the looks of that guy? He's nicer, agreed. What about this? I don't like this 2/3. Is there anything I can do about that? Actually, I don't even like the negatives, to be honest. Oh, and while I'm at it, why don't I just call that the cube root of t squared? Yeah. Right. How can you fix that to make it look a little prettier? It's a common factor.
Negative 3 out of it. Factor out then.
Negative, I didn't catch the last part.
3.
Is it 3 or 1/3?
Or sorry, yeah. Is it?
Now, if you do that, you're going to have 9 plus 2t. Check it out. Is negative 1/3 times 9 negative 3? Yep. Is negative 1/3 times positive 2t negative 2/3? It is. And you see that 3 guy? Stick a negative at the side and bring that 3 downstairs. And we are finished. Thankfully, these are not common questions, but they are ones that you have to be able to deal with, right? Where you're going to have to try and factor out a common factor that is a negative power. When are you going to likely see these? Only if there's square roots or cube roots in the original question. Then there's a chance that that might happen, right? If there's square roots and cube roots in the original question, then you might get to do this rather interesting math. And that's the answer. Are we good? Today's theme is product and quotient rules, but for ugly algebra. In that last question, I probably spent a minute differentiating and about the other 9 minutes doing all the algebra that went with it. Can you see that the proportion of what is not on the differentiation side isn't it on the algebra side? Just making it look pretty. So we are now going to look at finding first and second derivatives. In other words, multiple derivatives. And I'm going to do a relatively nice one to start with, and then an ugly one for the time that we've got left, hopefully 2. Here's a function. We would like to find its first and its second derivative. Nothing needed to be done. Would you agree this one is good to go? It's a product rule. Everything's fine. So its derivative is f dash g plus f of g dashed. Differentiate the first, leave the second alone. Leave the first alone and differentiate the second. Okay, common factors. Anything in this list that is a common factor that you can deal with? What can I pull out?
E to the
X.
Definitely. Anything else?
x squared.
And that leaves me with a 3x. No, it isn't. It leaves me with a 3 plus an x. I'll just rewrite that again. So we get this guy and a 3 plus x. And we're happy, right? No wrong with that. Went smooth. Now I want to get the second derivative. Uh-oh. One function, 2 functions, 3 functions. We're going to have to differentiate a function that's made up of 3 things multiplied together, not 2 things. You can have. Here is the product rule for 2 functions being multiplied together. Here are 3 functions. Imagine you're the first person to, hit this problem. Right? There's always going to be a first person for everything. And you're thinking to yourself that math tends to have patterns, and maybe there's a pattern that I could use to alter this so I could use it in this situation. And it's probably a guess, and it might be wrong, but that's okay. I'll take a guess. What do you think the formula for multiplying and finding the derivative of 3 things multiplied? What's the formula for its derivative? Only having this guy as a kind of template and trying to use patterns.
Function of f times g n times h plus function of g f and h and function of h f and g.
That could be correct. I'm not going to write it your way, but that could definitely be correct. Are they going to just be called f, g, and h, or are one of those going to be a derivative?
Yeah, sorry, I meant to say derivative of f and then derivative of g and then derivative of h.
So I'm doing exactly what you said. I'm just keeping the order the same, rather than put the derivative at the front. I mean, that's cosmetic. What you said was bang on. Does that seem reasonable? Right? Will you just trust me and Sabrina that we're right? And everybody else who thought, yeah, that's probably what I would have done. Right? So f dash gh plus f g dash h plus f g h dash. You're never going to get it, but couldn't you expand that to 4 functions? F, G, H, and I. Couldn't you just continue it to 5, 6, and 7 functions? Now, if you were the first mathematician to discover that pattern, it's not good enough just to write it down and use it as if it's valid. They would have to then do the proof of it, and that's where the fun starts. And we don't, we just use them. So differentiate this guy. and leave the other two alone. Leave the first one alone, differentiate the middle one, leave the third one alone. Leave the first one alone, leave the second one alone, and differentiate the third one. Okay, let's do common factors. What are the common factors in this expression that we can pull out of all three terms? What are the common factors we could use?
X and EX.
Agreed. Now, if you use up an x and an e to the x in this first one, won't you be left with 2 times 3 plus x, which I'm just going to multiply out? If you use up an x and an e to the x in this middle one, you've still got an x left over and a 3 plus x, so I'll multiply them. And in this one, if you use up an x and an e to the x, you still have an x times 1. You have that, which means that we now have an x squared, a 6x, almost missed one there, and a 6. And that's the second derivative. And I'm having a quick scan. No, that quadratic does not factor, so we are finished. And do you know all you do when you get a quadratic? Don't you try, what is that? 1 and 6 and 2 and 3. You know, that's the only two that would work. Do either of those ever give you 6x? No, so don't worry about it. So that was a multiple derivative of a product rule. Try to pick one that wasn't too scary. I'm now going to pick one that is scary. I'm looking for a rational function to do it to. I had one earlier. I think I'll pick one if I can't find one. No, darn it in space. Okay, this one will do. This is 26. And the function that we're going to work with is that. Okay, quotient rule, first and second derivative, that's what we're being asked to do. Let's get the first derivative done then. F dash g, take away f of g dashed over g squared. If you differentiate the top, leave the bottom alone. Subtract, leave the top alone, g dashed gets you 2x. All over x squared minus 1 squared. What do we have? An x squared, take away 1, take away 2x squared. All over x squared minus 1 squared. And collect like terms. Yeah, yikes. Ugly. Oh, that's an ugly looking fraction. I did that one a little bit quickly because the next stage is going to be messy and I want to have enough time to finish it. Are we okay with that one as far as it goes? Any questions about that? We feel good. Right, you know that the hard work is going to be on the second derivative. And this is the first thing I'm going to do. See this x squared minus 1 squared, which is really nice, and we like that. I've had to turn it into this. And you might say, well, why did you do that? And it's simply because if I'm going to differentiate this function, would you agree differentiating this is pretty easy? Would you agree trying to differentiate this is a non-starter? Can you see why I had to choose to do that? Only because I need to find the second derivative. So it's going to be f dash g take away f of g dashed over g squared. If you differentiate the top, you get negative 2x. Leave the bottom alone. Take away, leave the top alone. And differentiate this guy, and you get 4x cubed, take away 4x. And the whole thing is this guy, squared. Okay, let's work on this guy. Do you see this ugly x to the 4 minus 2x squared plus 1? See this guy here? And now he's squared. Isn't x to the 4 minus 2x squared plus 1, wasn't it originally just x minus 1 squared? Great. That this is just that multiplied out. So won't this be x squared minus 1 squared squared? There. Do you see how I made the bottom pretty again? I turned it into this ugly form of that, only so I could use it to differentiate. But once it's done its differentiation job, right, get it back to being pretty. What do you think I'm going to do with this? I mean, this numerator, what on the earth are we going to do with that?
Foil it all out.
Yeah. Can you see why I had to do the first one a little bit quick so we'll have enough time to do this? So negative 2 times this and then follow that one. So negative 2 times this is negative 2x to the 5. Negative 2 times this guy is plus 4x cubed. And negative 2x times this guy is negative 2x. Oh God, there's negatives everywhere here. This guy times this guy and then make it negative. So it's negative 4x cubed, but then you subtract it. And it's not cubed, it's 5. Right, this guy times this guy is positive 4x cubed, but then you subtract it. This one times this guy is negative 4x cubed, but then, check that, negative 4x cubed, but then you subtract it. And the last one is positive 4x, and then you subtract it. This term and this term get me 2x to the 5. This term, and this term get me 4x cubed. This term and this term get me negative 6x. Okay, anything I can do on the top as far as a common factor goes?
2x.
Agreed. That leaves me with an x to the 4, take away a 2x squared minus a 3. I'll do this in a side issue. You are now going to see something that some of you probably have seen before. That isn't a quadratic, right? It's got x to the 4s in it, but it can still be factored. And it can be factored. It's a trinomial, and it's x squared and x squared. And that's where the x to the 4 comes from. And I am looking for two numbers that multiply together that give me -3. But when I add them or combine them, I get -2. And would you agree that -3, is that -1? Something's not right.
Positive one?
Something's not right. I know what I need, and I'm not getting it. That's what my problem is. I need this to be plus. I need this to be plus. So maybe I did it up here. Would you look at it? There's my mistake. See it? It was plus. Whew. Start again. This guy is plus 2x squared. It factors. And now I can get the combination I wanted to get, which is that combination. Now you might say, well, how did you even know that it was wrong? Because the other one worked fine, right? Well, I kind of know it does, because if this guy factors as this guy, now what do I have? I have 2x, I have an x squared plus 3, and I have an x squared minus 1. Are you okay with trinomials that look like this can also be factored? Right? X to the 4 gets you x squared and x squared. Two numbers that multiply together give you -3, and when you combine them, you get +2. I mean, it's a bit like someone saying, can you factor this guy? And you should be able to say, yeah, I've done tons of them, right? Well, isn't y like x squared? You see, same math, right? Well, why is that good? Well, won't one of these cancel out one of these? And so what you're left with is a 2x, an x squared plus 3, all over an x squared minus 1 cubed. And we now have a very elegant, nice looking second derivative. Well, come on, look, it's much nicer looking than it did up there. Agreed? Look at where it started, and look at where it's now finished. So your algebra skills are going to be so good by the time you finish Calc 1, because you are going to get, hopefully, really good at factoring things and making them pretty. So say hi and bye-bye.